FaceTime seems to be doing a slightly odd thing with clipping my face, but anyway, I just wanted to say hello. I'm Edward Lee, and I'm going to be showing you around how you extend Ptolemy 2. And I'd just like to start by just giving you a quick reminder of some of the topics that we discussed in the last session. Okay, in particular, what is Ptolemy 2, in case you weren't here or are just being exposed to it for the first time. So it's about heterogeneous modeling and design of complex systems. There's a very strong emphasis on using well-defined models of computation that achieve deterministic behavior of concurrent systems. And key thing to understand is that really the main goal of the Ptolemy project in creating Ptolemy 2 is to create a laboratory for experimentation. And this is the emphasis of today's tutorial, is in fact on how you use this laboratory for experimentation. In other words, what you can do to leverage the open architecture and make extensions to the system that are that really can be quite fundamental. So it's an open source system, and here are some stats on it, but I'm going to not bore you with those details at the moment. Instead, what I'd like to do is start by just reminding you what we did last time. And roughly 1 week ago, last Wednesday, we went through a tutorial where we constructed a model from scratch. And this is a variant of that model. I mean, we were pretty close to this version at the end of the last session, but I've gone through and done some things that are advisable generally in models, such as adding comments that explain what the model is, putting a title on the model, adding parameters that we didn't originally have so that you can parameterize the model in interesting ways, attaching annotations to components that explains what they're doing, and putting in an annotation that also then shows the parameter values that have been overridden. So this is useful for documentation. For example, if you print out a model, it's useful to know what the parameter values are of the components. So to remind you what this model is, it's a model of a simple cyber-physical system that consists of a continuous time model of a generator, and this was meant to be a generator with a, say, a gas-powered generator where you could control the throttle, and the output voltage would respond in some way to that control of the throttle. And what we did was we built a simple linear time invariant system with first-order dynamics to model the generator ramping up when you open up the throttle. Here I've added a nonlinearity as well, so illustrative that you can combine nonlinear and linear behaviors in these continuous time models. And this model has also elaborated a little bit on how the load is handled, but you can attach a load to this generator. Then, in addition to this continuous time model of the generator, we have a discrete time model of a controller, in this case a simple PID controller, which is a proportional integrator derivative controller. And what this controller does intuitively is just compare the voltage that it's getting from the generator with a desired voltage and then issue a correction signal. So this is a sample data system, and this model is suitable for code generation. So you would take this part of this model, if you were going to deploy this system, code generate this to deploy on an embedded processor, and that would become your discrete time controller. In addition, there's a supervisory controller that is gating the connection and disconnection of the load to this generator. And in particular, this supervisory controller is designed to protect against an overvoltage condition. So if the generator produces a voltage that is above a threshold, which is a parameter in this case, then the supervisory controller will disconnect the load to protect the load. And this model is a finite state machine model that has two states in it and will transition from on to off when you either get the false condition, meaning you're protecting the load due to overvoltage, or you've issued a disconnect command. If I execute the model, I get now a nicely annotated trace. This is the other thing I added since last week, was just properly labeling the plots. Okay, and you can see what's happening in blue. The voltage is ramping up initially to the target voltage of 110 volts. The throttle control signal to the generator is shown in red. When the load gets connected, this is a very heavy load, and so the voltage instantaneously drops in half. The controller opens up the throttle to bring the voltage back up, overshoots, hits the threshold for overvoltage protection, disconnects the load, causes the voltage to shoot up, and the controller brings the voltage back down, 110 volts. Okay, so this is a use of Ptolemy where everything was built from I'm hearing birds chirping in the background. Does someone have birds in the background?
No, I'm muting. I'm trying to mute people. Hang on.
Okay.
I've lost one of the menus. Keep going. Oh, there we go.
So this is a use of Ptolemy where you're just building things out of pre-existing components. Okay. It's a heterogeneous model. So you notice it's a discrete event model at the top level, as indicated by this discrete event director. It includes a finite state machine, which is another kind of model. It includes a continuous time model, which has a different director in it. And it includes a discrete time model, which in this case is using a data flow director. So this model is combining 4 different models of computation.
Edward, I have a question from a remote question. The question is, does Ptolemy contain the ability to actually create the embedded code?
Very good question. So the question is code generation. So in particular, if you want to code generate this controller, does Ptolemy include a capability for doing that? The answer is yes and no. We have done quite a bit of research in code generation and have actually gone through several different generations of code generation infrastructure. And there is a code generation infrastructure in Ptolemy that in principle is capable of generating code for models like this. It's quite immature right now and requires some investment to be fully usable. So the answer is sort of. Okay, so what I'm going to focus on today is on not building models out of pre-existing components like this one here, okay, but rather creating your own components. And I'm going to show you how to create 2 kinds of components. I'm going to show you how to create actors, which are these components that participate in a model, and I'm going to show you how to create directors, which will change the model of computation, all right? I should advise you that it's pretty challenging to do that within a 1-hour time slot, okay? And there's a couple of pieces of what I'm going to be showing you that involve a fairly steep learning curve. And what you're going to see me do is what you can do after you've overcome that learning curve, okay? So to some degree, there's 2 things that you will really need to internalize before you can replicate what I'm going to do today at the same speed, okay? One of them is using Eclipse, which if you're already an Eclipse user, that's great. But Eclipse itself has a fairly steep learning curve, but it's an incredibly powerful tool. The second one is just getting familiar with the API in Ptolemy. And I'll show you that, in fact, Eclipse helps you a lot. I personally have a very bad memory, and Eclipse helps me remember aspects of the API that I can't carry around in my head. So I'll show you how these 2 tools can actually work together in conjunction very nicely. Now, I'd also like to point out that there is a lot of example code to look at. You can pick any particular actor, for example, and just open it and see the source code. And you'll see in the source code there is quite a bit of comment. I strongly advise commenting your code, please. I am going to violate that rule today because, first of all, writing comments takes a lot of screen real estate, so you'll have a little bit of trouble seeing the code if I put in a lot of comments. But secondly, I don't type very fast, and it'll really slow us down if I put in comments. So I'm gonna write uncommented code. Please forgive me for that, but that's what I'm going to do, okay? But the code that you'll see in the tree is all extensively commented, and you can look at the pieces of it. The comments play a role not just in the code, but they are also used to automatically generate documentation. So if you right-click on a component and you say get documentation, you get a description of the component, okay? Here's its icon. Here's a description of its behavior. Here's a description of its parameters. Here's a description of its ports. Most interestingly, there's also a See Also box, which is created automatically again. And perhaps the most useful of these is the demo usage link, which is a list of all of the demos in the tree that use this particular component. So you can click on any of these links and go to an example model that uses this component. And so it's a nice way to get a sense for what it does. So commenting the code is extremely valuable. That said, I'm going to not do that. So let me start then with actors. And what I'd like to do, here are some actors, okay? But these aren't the kind of actors that we're going to be creating, okay? The kind of actors that we are going to be creating are software components. And I'd like to explain the use of the word actor here, because I think it's important to understand what we're doing here. So in software engineering, when people talk about software components today, they almost always mean objects as defined in today's object-oriented programming languages. And objects are software components whose interface is primarily procedures that are called methods in the object-oriented community. So the way that you compose components in object-oriented programming is you call procedures of components and you get return values, and those procedures may modify the state of the component, okay? So the way that you string together components, the way you compose components, is sequential intrinsically, because it's a procedure call semantics, okay? You transfer control to an object by calling a procedure, and you block until that procedure returns. Now, of course, there are various extensions to object-oriented programming to create, for example, active objects. These tend to be highly non-deterministic models of computation. Actors give you a different way of complementing the object-oriented design with concurrent models that can exhibit deterministic behavior. So the key thing about an actor is that instead of its interface being procedures, its interface is primarily ports. And the idea is that ports receive a stream of changing data. There's stimulus from the environment of the actor, and the actor reacts to that stimulus and produces stimulus on output ports. And the way that you compose actors is by taking an output port from one actor and connecting it to an input port of another. And now, conceptually, those two actors are executing concurrently. They're doing their thing at the same time. One is producing stimulus, the other one is reacting to that stimulus, okay? Unlike, say, active objects, you can, however, impose a discipline on these, this composition of actors so that you get deterministic behavior even though they're executing concurrently. And that's a big emphasis in Ptolemy, is to be able to do that. Okay, now, the API. In order to create actors, you need to internalize certain things about the basic structure, the software architecture in Ptolemy 2. Here's a very simple abstracted UML diagram, and you can find in the Ptolemy documentation much more detailed UML diagrams that show, very compactly show the API for the components that we're looking at. But this is almost enough to do what we're going to do, okay? So actor is an interface in Ptolemy, and it extends a simpler interface called executable. And we're going to focus on just the first two methods in this interface, the fire method and the initialize method. So initialize is used to initialize a component. The fire method is used by a component to react to inputs and produce outputs, okay? So for today, that's all we're going to use, is fire and initialize, and we're going to create actors. Now, there's various components, there's various classes that implement the actor interface, and there's a hierarchy of these, but atomic actors and composite actors both implement the actor interface. So composite actors are themselves contain an interconnection of actors. atomic actors are individual Java classes that implement some piece of functionality. And I'm going to show you how to create atomic actors today. Okay, so before I start into the coding, I would like to show you what we're going to build. All right. So here is an example from the Ptolemy tree of a very simple model that's created with an actor that is very idiosyncratic called a smart sender. It's a very strange actor. It's not one that you would normally include in a library because its behavior is just too weird. You know, it's a one-off thing. You're going to use it for a specific purpose. What it does, initially is very simple. So I'm running the model. So the smart sender has a parameter which is its firing period, which is set to 0.5 for all of these actors. So what this means is that it will produce events with a spacing of 0.5 seconds between them. Now, you can see that it's producing a counting sequence. These monitor value actors are just displaying the latest value received by this smart sender. You notice that they're actually producing them at 0.5 seconds per value, and the reason for that is that I've selected a parameter in this discrete event director that is labeled synchronized to real time. Okay? If I deselect that, the model starts executing much faster because it'll execute faster than real time, and I probably shouldn't have done that because now it's the UI has to catch up. I may have to kill the model and start it over again. One of the problems is that you get an accumulation of events in the event queue that will, yes, I shouldn't have done that. One should never improvise when doing demos. My machine is also getting kind of warm in my lap.
Wait, did it come back?
It's thinking about it. It will eventually come back, but there's a long queue. What's happening actually right now, and it's worth discussing this because this happens sometimes. In Java, the user interface is single-threaded, okay? There's an event queue that is shared by all Java programs that are running, and monitor value is using events from that event queue to update its value. It's the same event queue that's reacting to the buttons that I push on the screen, okay? So let's see what happened to the model. I have lost it.
Yeah.
But it's still executing. Oh, I got the, yeah, we need to get it to stop. I can kill this process and start another one, but it, never improvise when you're doing demos. Come on, stop. I think my event queue has simply gotten too long. This phenomenon will only occur when you're using actors that are, in fact, actively doing displays in the user interface, because these are the ones that are actually handling events in the event queue. But I apologize for this.
Do you want to kill it from the shell?
Yeah.
Or
Okay. All right. Here we are back at the smart sender, and it's running again. producing samples at a period of 0.5 seconds, okay? And I'm not going to turn off synchronize to real time again. Okay, now, so far, this doesn't seem like such an idiosyncratic actor, right? Because it's just producing a counting sequence. That's pretty boring. But the weird thing about this actor is that if I disconnect it, it reconnects itself. In fact, I can disconnect all of these while they're running, and they will reconnect themselves. Moreover, I can create a new instance of this actor by just copying and pasting, and it just sits there doing nothing until it finds something it can connect to. So I'll create something it can connect to by copying and pasting this. And lo and behold, I've got another component that is now gotten connected, okay? So if I create one of these guys with nothing to send to it, then it just sits there without receiving any data. But if I create a new instance of this smart sender, it connects, it finds something to connect to and connects to it and starts executing, okay? So that's bizarre, right? And this is the kind of thing that I mean by, it's something that you might be interested in doing in extending a system, is to create something like this that in fact is sort of working with the dynamic structure of some model. So I'll show you how to create an actor like this from scratch, okay? So, Eclipse, my preferred development environment. Lots of people use lots of things for developing Java programs, but I think if you're not an Eclipse devotee, you might be by the end of this, okay? So there's a fair amount of setup to get Ptolemy integrated with Eclipse, but the details are on the Ptolemy website for how to do that, and it's reasonably straightforward.
We have two questions here. The first question is, how far does it look within the address space or across the net? I think the question is like, where does it look for to connect the sender? Where does it look for something to connect to?
Well, we can control that because we're going to define the sender, but what I'm going to do is I'm going to define the sender in such a way that it only looks for it's going to look for an unconnected input port that is at the same level of the hierarchy that it is at. Okay, so it's just going to look for an unconnected input port at this level of the hierarchy. But you can do whatever you want, right? You can go and look up in the hierarchy, down in the hierarchy, etc.
We could have an actor that represents something on a different machine, say, and connect via the net.
You could, although that's going to require some director work. Okay. This director manages, so the director is in charge of two things. The director is in charge of executing the actors and managing the communication between actors. Okay. This director will only manage communication within the same machine, and in fact within the same Java virtual machine instance. Okay. But people have created Ptolemy directors that will execute models on multiple machines simultaneously and will manage the communication across machines. There are in fact several of those. There's some in the experimental directors library here in particular. Maybe they're not there anymore. In any case.
A second question.
We do have some instances of examples like that.
A second question is it possible to use Ptolemy as a component of an embedded system to take advantage of the smart sender concept?
So again, the Ptolemy system is designed for experimentation. So there's a lot of things in it that are for the convenience of experimenters. So I like to think of it as a laboratory infrastructure. So just like, a physicist, an experimental physicist who does a lot of, puts a lot of effort into the design of an accelerator in order to perform an experiment. Ptolemy is our accelerator for performing experiments. You probably wouldn't deploy an accelerator into an airplane, for example. So our strategy generally has been that you code generate from Ptolemy models to create much smaller realizations of models rather than deploying the models directly. Now that said, there has been some experimentation. So for example, some students at CMU created an infrastructure where you could have a Ptolemy model where part of it would run on an Android phone and the other part would run on a server somewhere, and they would communicate. So they were actually executing a Ptolemy process on the Android phone, so it is possible to do that.
Okay, there's actually a follow-up question to the first question, and the question follow-up is, what protocol does it use for the connection? So I guess really two parts, like what protocol are you using here, and what protocol are those students using?
So here, the protocol is managed by the director, and I'll actually show you how the communication works. So you'll see what the API is, and you'll see that in fact you can define your own protocols as long as they're consistent with this API. Okay. Now, so what protocol the students were using? What were they using?
MQTT.
MQTT for the communication from Android to the host, which is an XML-based communication protocol. That is entirely behind the scenes from the perspective of the model builder. The model builder still just makes connections between actors, and in their case, the director handles that instantiation of the communication infrastructure to handle the transport. Okay, and I'll show you how that works shortly. So, okay, so we're going to create something like this smart sender, and I'm going to do it from scratch. Okay, so in particular, I'm going to start with a whole new package.
Actually, I have one other question. Interestingly, Ruzba Jafari is experiencing the telecon from an airplane. That's why I made that bad joke. He's literally at 30,000 feet, and so this is kind of a first for me that WebEx works on an airplane. So Ruzba asked, can we introduce probabilistic delays and investigate if that might create instability issues for the system? And I think then he says in communication lines. So can you have probabilistic delays in the communication lines and look for instabilities in the system?
Absolutely. Yeah, it's a big part of what we do. In fact, the discrete event domain is very convenient for doing that. And one of the current efforts in Ptolemy is to actually make it so that you can couple together a model of some piece of functionality, such as the controller that I showed, the generator controller, together with a model of your communication network, and evaluate the effects that the parameters of your communication network have on that controller. That's a little bit of a big topic, and I am afraid it's out of scope right now to go into that in detail. But Ruzba, I would be really delighted to show that to you at another time.
Okay, so let's proceed.
Okay, so in Eclipse, I'm going to create a brand new package, okay, and create an actor and a director in that package and instantiate them in models. So as a general convention in the Java world, it's a good idea to name packages based on your domain names for your institution, okay? So if you're eal.org, okay, by convention in Java, you reverse the order, and you name the package org.eal, okay? EAL is my initials. I don't actually have that domain, but I'll pretend that I do, okay? And this helps to avoid collisions between package names so that lots of people can contribute to a software infrastructure without having their packages collide with one another in the namespace, okay? So I'll create a package called org.eal, and there's a package called org.eal, which has nothing at all in it. So let's create a class in that package, and I'm going to call the actor that I'm going to create Precocious, okay, because it reaches out and connects to strangers, it's going to be in this package org.eal. And the first question I have to answer is, what should its base class be? Okay, so the base class for most actors in the Ptolemy library is typed atomic actor. Okay, the browse button in Eclipse is very handy because I can type the beginning of a class name, maybe I don't remember the whole thing, and it will find the class and identify the class that's going to be the base class. Then I can also choose to include constructors from the superclass, which will save me a bit of typing. Okay? I can choose to generate comments, which will really only, I mean, that's a little misleading. It doesn't actually generate comments. It just generates the template for comments. But I'm not going to do that because I'm going to economize on screen real estate. Okay? Finish, I can create a class. Here's a class called Precocious that extends typed atomic actor. It has 3 constructors that it inherited from the base class. And one of the things that's useful to know in Ptolemy is that you really don't need the first 2 constructors. They're there in the base class for running regression tests. They're not there for end users, okay? So you really only need the 2-argument constructor. And the 2-argument constructor just says, when you create an instance of Precocious, it should have a container and a name, okay? So the container is a composite entity. So when you create an instance of this, you would normally put it inside a container, and that's all you need to do. Okay, now I want this actor to have an output port. So our output ports, by convention in Ptolemy, we make them public fields. Okay, so if you look at the interface to an actor, you'll see a public field that is the input and output ports. Okay, so and ports are of class typed IO port, and let's just name it output. Okay, now Eclipse tells me immediately that there's a compile error. Okay, it doesn't know what a typed IO port is, and that's because the import list doesn't include typed IO port. So I can use this quick fix, and it found a typed IO port in the library. But there's an even more convenient thing in Eclipse. If you go to the source menu and say organize imports, then it finds everything that is undefined, nicely alphabetizes your import list, and in this case, there were no ambiguities anywhere in scope. There's only one class called typed IO port, so it was able to unambiguously import that. Okay? So now I've got this public field, but I don't yet have a port. I have to instantiate the port. Now here, I'm going to apologize because, you know, for those of you who like designing programming languages, you'll see that this way of defining actors is very verbose. Sorry about that. We actually have had some research projects in defining actor languages that are much more compact. Our experience is that people don't like learning new languages. They would rather use languages that they are familiar with, even if they're very verbose. So I'm going to show you the raw mechanisms here and not the more advanced actor languages that we have experimentally developed. And so this is just straight Java code. So to instantiate the port, I just set the public field equal to a new instance of typed IO port, and I will specify a container for that port, which is this actor, and a name, which is output. Okay, so notice there's a pattern. The actor itself has a constructor that takes a container and the name. The port has a constructor that takes a container and the name. In fact, just about everything you would invoke in Ptolemy has a constructor that takes a container and a name. Okay, so this creates an instance of the port. Now, I can go ahead now and instantiate this actor already in a Ptolemy process, and it's most useful to do that within the debugging environment of Eclipse. So in Eclipse, I am going to show you how to create a debug configuration that will start up Virgil and then run the graphical editor from within the debugger. Okay? So I can just go to this little bug up here and select debug configurations, and I would like to create a new Java application, which it names by default new configuration. Let's give it a better name like tutorial. Okay? And I have to identify a Java class that has a main in it in order for it to invoke the program. I don't remember what the Java class is called, so let me just type the name of the graphical interface Virgil, and then do a search. And it searches the tree for everything that mentions Virgil that has a main in it. And lo and behold, its first suggested hit looks pretty promising, a Virgil application. So I'll select that. And
you need to change the name of the app. You have a configuration already exists.
Oh.
Change it to tutorial 2.
Okay. I already have something called tutorial. All right. So I'll call it tutorial 2. And then thank you, Christopher. And then I click debug, and it will invoke Virgil, okay, within the debugger now. So now I can create a brand new model and instantiate my actor. So I go to the graph menu. Now notice, I mean, my actor is not in my library anywhere, of course, because I haven't done anything to put it in the library. But you can instantiate things that are not in your library as long as they're in your Java class path. So I can instantiate entity, and the name of the entity is org.eal. What did I call it? Precocious. And lo and behold, I have a component. It has a port. Interestingly, the port is rendered as a circle, which is the graphical notation for a port that is neither an input nor an output, because I actually haven't specified whether it should be an input or an output. I can look inside, and I'll see my source code, okay? But this isn't going to be very useful yet. So let me just save this model so that I don't have to go back and reinstantiate this, and then close this and elaborate on this model a little bit to create something a little more useful. Okay. So the first thing is I want to make this port an output port. So Eclipse helps me remember how to do that by just doing kind of suggested auto-completion. Okay. So if I can't remember what the API is, again, just to do this, I can just say output dot, and then if you hit Control Space, it says no templates suggested. So if I say, well, set, what are all the set possibilities? Whoops. These are all the SE possibilities. These are all the set possibilities, all the set O possibilities. Okay, set output. That's the one I want. All right, so I set it to be an output. I can also specify that it has a particular data type. Okay, and in fact, I will need to specify a data type, otherwise it won't be able to infer, in this case, what the data type is. So I can say, here are all my set type possibilities. You can specify type relationships, or I can just fix the data type. And again, here's where there's a bit of a learning curve to learn the API, but once you've got it, it's pretty easy to see how you set a data type. So here I'm going to set the data type to int. Base type is an unrecognized class. I can say organize imports, and it found 2 hits for base class, one in Sun's code, in the built-in Java code, and one in the Ptolemy code. So I should choose the one in the Ptolemy code, and now I have a port that is in fact going to be an output port. Okay? Now, so far this actor doesn't do anything. So let's have it produce a counting sequence. So to produce a counting sequence, I'm going to need a private variable to remember the count. Okay? And I'm going to need an initialize method to initialize the count. Now, as a general practice, when you override, this is overriding an initialize method that's provided by the base class. It's a good idea to always call the base class initialize method. You don't have to, but there's a certain built-in features that are convenient for debugging that are provided by the base class. So it's a good idea to do it, okay? And you notice I get a compile error. And the reason I get a compile error is that the superclass initialize method throws an exception, and my initialize method does not. Fortunately, Eclipse suggests a couple of fixes. Okay, I can hide the exception, usually not a good idea, or I can add a throws declaration, better idea. Don't hide exceptions. Okay, and now this compiles. Okay, now let's produce output. So I can create a fire method, call the superclass again. I get the same compile error, add a throws declaration, increment my count, and then produce an output. Whoops. So output.send, and again, Eclipse can remind me what I need to do. Okay, it looks like the first send will do. I need to specify a channel index and a token. So in general, with ports, you can have multiple output channels. The first channel is numbered 0. And now I need to create a token, which should be an integer token with value count. And again, organize imports. And I now have an actor that should produce a counting sequence on its output. So I can reinvoke my debugger by just clicking on this debug menu and open the file. What did I call it when I saved it? Model. And notice now Precocious is instantiated, and now it has a port that is properly indicated to be an output port. And now I can wire up this model wire up this actor in a model, for example, to do something like display the output, okay? And to avoid running forever, let me specify a finite number here. And lo and behold, you can see that, in fact, it generates an output sequence with 100 output values. Now, what I wanted, however, was an actor that would produce a sequence once every 0.5 seconds or so. So I could do that with the discrete event director, okay, with its synchronized to real-time parameter set to true. However, if I run this model, it immediately stops executing because there's no triggers to this actor. And in the discrete event model of computation, unless an actor is triggered by an event, it doesn't fire. So I have to modify this actor in some way to cause it to be triggered, okay? So in the initialize method, I could modify this and say, I would like the director to fire this actor at the time of initialization, okay? So this is what this means. I get my director, and I request a firing at the current time of myself. And I did that in initialize. So if I go back to my model now, this is the nice thing about working in the Eclipse debugger, this model will now, in fact, produce one output. Because in its initialize method, it requested a firing, and it got fired at the time of initialization and produced an output. But then it didn't request any further firings, so it stopped at that point and was basically done executing. So I could go in to my fire method and request a firing there, also at the current time, okay? And now I better be careful to avoid this problem that I had before. Let me specify a finite execution time of, say, 100 time units, okay? And actually, that's not going to stop this model. Interestingly, the model just keeps running because nothing is advancing time, in fact, in this case. All of these events are getting produced at initialization time. If you remember, last time I talked about the superdense model of time in Ptolemy, what's happening is we're getting an infinite sequence of events at time 0 coming out of this actor. So I don't really want to fire at current time in the fire method. I want to fire at a future time. For example, I could say fire this actor at the current time plus some number, say 0.5, okay? So there, that's requesting a firing at the current time plus 0.5. And now if I go and execute this model, I will see that in fact it is producing events. Now because synchronized to real time is set to 0.5, it's actually producing events every 0.5 seconds and displaying them accordingly, okay? Now, I don't want a hardwired number in my code. That's generally bad practice. So what I'd like to do is create a parameter that is the period, whoops, and instantiate the parameter in a similar fashion. Okay, organize imports to find the parameter object, set the type, and, whoops, set a default value of, say, 1.0, okay, and save my model. And now I get an interesting phenomenon. When I go to save this, Eclipse warns me. Why? Because I've just added code to the constructor, and in the executing process, there are instances of this object already. Their constructor doesn't get re-invoked, and therefore I need to actually reinstantiate these objects. So I can do that by, actually, let me continue first and, whoops, save the model, okay? And it actually might work to just reinstantiate. Never improvise while you're doing a demo, but I'm going to do it anyway. I will reinstantiate this object. Hopefully that invoked the new constructor now, okay? And in fact, no, it didn't. So it invoked the old constructor. So I really do have to, yeah, it doesn't actually replace the type. Okay, so I have to reinstantiate the debugger.
Typo. I'm saying the typo expression.
My class definition didn't even compile. Okay, so obviously Eclipse was at a loss. Okay, so let me do one little shortcut here. I can also specify program arguments in my debug configuration so that I don't have to go and find my model file. So now Precocious has a period. It's set by default to 1 second, okay? If I change it while this is running to 2 seconds, it should slow down. Oh no, it doesn't slow down. Why not? Because if I go and look at my code, I still have my hardwired 0.5 in here. I didn't use the parameter value. So let me get the parameter value. And again, here, things are more verbose than one would like. But once you get familiar with the API, it's pretty easy to use. And double token is not recognized. Organize imports. Set the value. Go back to my model. Execute it. Now I find, in fact, it's running rather slowly. Okay, producing events with time 2 seconds between events. I change it to 0.5, and it'll speed up quite a bit, and so forth. Okay. Now, so far I haven't actually made this precocious. Okay? It's not doing anything about reconnecting. If I disconnect it during execution, it's just going to stay disconnected. So let me go back to my fire method. And here, what I would like to do is, instead of just sending an output, I would like to send an output if I'm connected. If I'm not connected, get connected. Okay? So if my output is connected, send an output. Otherwise, I want to get connected. Okay? Now, you can well imagine in a concurrent model of computation that it would be very dangerous to mess with the model structure in the fire method of an actor. Okay? You can't just connect to something, because this actor is executing concurrently with a bunch of other actors. The connection process could put the model into a transient, unstable state, and when it's safe to actually make the connection isn't really known by this actor. In fact, only the director can know when it's safe to do this, because the director defines the model of computation. So the API includes a mechanism to request that the director make a change in the structure of the model when it is safe to do so. Okay? So that's the mechanism that I'm going to invoke. So the way that I do that is I create an instance of a class called changed request, and I'll name it request. New change request. And Eclipse helps me remember what the API is, and I can specify a source and a description. Okay? Make connection. And then Eclipse also helps me to fill out what I need to do further, which is that there's an abstract method in this change request that I need to populate. So I create an instance of a change request, and then I simply request a change. Okay? So what will happen now when the fire method gets invoked is, if the actor is not connected, it will request a chunk of code to be executed when it is safe to change the structure of the model. So here, in the body of this execute method, I can put in code to change the structure of the model. Again, I'm going to go rather quickly because, again, you have to sort of get familiar with the API in order to do this quickly. But once you're familiar with the API, you can really do this rather rapidly. All right? So in particular, we can do I know that my container, because of my constructor takes a composite entity as an argument. So my container is a composite entity. Okay? So I request my container. Eclipse tells me there's a compile error. It suggests some fixes. A cast will work. It's a safe cast because the constructor only takes a composite entity as a container. Okay? The container, because it's a composite entity, has a list of the entities it contains. Okay? Whoops. So organize imports. It suggests a list and an entity. And now I have a list of entities contained by the container. I can now iterate over each of those entities. Okay? And similarly construct a list of their ports. Organize imports. And iterate over the list of ports. And now, if I find a port that is an input port, and is not connected, then I will connect to it. Okay? So again, I created that code rather quickly, but once you're familiar with the API, you can really do this. You just iterate. I'm just iterating over the structure of the model. I ask the container what objects it contains. I ask those objects what ports they contain, and I connect to an unconnected input port when I find one. So now, hopefully, rerunning this model inside of this will still work. If I disconnect, nope, I think I need to reinstantiate for some reason. So unless there's a bug in my code. Does anyone see a bug in the code? Does anyone see the code? Yeah, there it went. And notice that when it reconnected, it also missed a sample. And the reason is that there was a fire method that got invoked that produced no output, even though the count was incremented. Okay? So now I can actually create another instance of this by just copying and pasting, create another instance of the display by copying and pasting, and it connects to it and creates a new display. Okay? And so forth. Okay. So the next step is to create a director, but I'm afraid that we're not going to have time to do that today. So we're going to have to, I'm going to have to schedule another time to do that because we're at the 1 hour limit. Hopefully we can do that, and I can schedule probably a somewhat shorter one session that would go through how we create directors. The key idea in creating directors is that you can completely change the semantics of models. And in my experience, the first thing that most people want to do is take a deterministic director and make it non-deterministic, something that I don't particularly like, but people seem to insist that they want that until they get enough experience with it to realize that that probably wasn't a good idea. But nonetheless, people like to do it, and this environment encourages experimentation. Therefore, we encourage such experimentation. And in the next session, which we'll have to schedule, I'll go through how one creates a director from scratch and modifies the behavior of models in a very fundamental way. So let me just close by giving you some pointers to some useful resources. Oops. A book, which is in draft form currently, a three-volume set of documentation. The middle volume, volume 2 on software architecture, is the most useful one for doing the kind of exercise I did today, because it goes through the API in quite a bit of detail, and it has some nice class diagrams that summarize a lot of information about the API on a single page, so you can get a feel for what it is about. And there are links on this page to those items. So if there are any questions at this point, I'm happy to host them. Otherwise, we will call this done and schedule another time to go through the process of creating new directors.
Any questions from our studio audience? Is everybody, who here didn't use, who here hasn't seen Eclipse before and now is like, huh, maybe I should use that instead of Emacs, and, yeah, and it's kind of cool. Does anybody here use NetBeans? So we had 2 people who are interested in Eclipse and 1 person uses it. A modern UI can be a good thing. Okay, so I think then let's close this. Thanks very much, Edward.